Hello, we're just connecting audio to do a setup check for tonight. Hi, actually, some of you are probably a bit surprised to see me here this early. In fact, this is because we're doing the session together with National Museum of Mathematics, so we're in fact setting up the equipment a little bit early. So if you're here early in the chat, you'll get to see what I'm saying, one side of the conversation. Hi, everyone. Did that get through to you guys?
Need to tell people if they're in the MOMAT site that they have to turn off the audio from one or the other.
Oh yes. So the way that we always do this is that they have to turn the audio off on the Zoom. Right. So they turn the audio off on the Zoom. Let me turn the audio off on the main thing. I'll see you guys in a little bit.
Well, wait a
so that we can be testing this, because then I'm going to try to make it so that the sound goes only through there. Just a second. Oh, actually, I'm hearing something. Oh, you know what? So, what's that?
I said you are, after all, a Carnegie Mellon.
Yes, yes. This should work. So I should be able to get this guy going through. This should work. So I should be able to get this guy going through. Are you hearing that come through?
Yes,
Yeah,
but it
very
senses.
hard to hear.
Are you hearing that come through? Oh, I am hearing this part. Just a second.
Yeah, very hard.
One moment. How does this work? Meeting controls. One moment. How does this work? Meeting controls. Leave computer audio. Excellent. That's what I want. Okay. Audio settings. Excellent. That's what I want. Volume to 0. Audio settings. Excellent. Volume to 0. Huh. That's what I wanted. Okay, excellent. So that should do it. So now I have a question. Are you able to hear me talk? Okay, excellent. So that should do it. So now I have a question. Are you able to hear me talk? Excellent. So that should do it. So now I have a question. Are you able to hear me talk? Are you able to hear the YouTube audio come through the Zoom? Are you able to hear the YouTube audio come through the Zoom? Okay, so now the YouTube audio should be coming through the Zoom. Is this working? Actually, here's a test now. So if you can help to look on this. Yeah. So what I'd like to do is I'd like to find out if I'm talking like this, if you can close the YouTube one. So Cindy and Don, if you could try closing down the YouTube and then just watching the Zoom. I'm curious if you can see and hear everything. So now the funny thing is I can't hear you. So now I should be able to fix that a separate way. So now the funny thing is I can't hear you. So now I should be able to fix that a separate way. So are you guys able to hear me on the Zoom? Oops. So are you guys able to hear me on the Zoom? It looks like Zoom crashed. Hang on. It looks like Zoom crashed. Hang on. Yes, hello. So this is back. I'm gonna do another share screen.
Actually, he's muted and video off. I think I might have to do that. Okay, I have unmuted him.
Yeah, okay. And I'm putting it back. So did the YouTube thing continue to go through or did it stop? This is back. I'm gonna do
Okay, I've enabled audio for Po-Shen, but video prompts him to open it himself. Oh, we'll start video later.
I'm actually just curious if this thing will go through. So, just a second.
Also, very low volume.
Right. Because I'm trying to send all the volume through that way. Leave computer audio. That's what I want. I'm actually just curious if this thing will go through. So, just a second. Right. Because we're trying to send all the volume through that way. Computer audio. That's what I want. Are you guys getting both the sound and the video through the Zoom at this point or no? Wow, seems like that's not the case. Hello everybody, I just realized that the whole section there was with no sound. That's because the setup tonight is different from usual. In fact, tonight is an event that is supposed to be run at the National Museum of Mathematics in New York City, which is somewhere that I go every few months because of the great work that they do. It just so happens that unfortunately it's not possible to go to New York City right now, and so we're running their session online. Because it's online, this is a way that anyone who likes to follow the things that I do can drop in and see. And so you're welcome to sort of get a window into my world. But I have to apologize to everyone. I'm not able to look at the YouTube chat tonight because this is an event that was supposed to be at the Museum of Math. So in fact, you often hear me referencing the Zoom conversation. That's because the Museum of Math organized their session as a Zoom meeting. So if you're here with the Museum of Math, I'll be talking to you directly through the Zoom channel. If you're here separately, you're of course welcome to just watch. And I'll put a plug for the Museum of Math. If you're in New York City and looking for something to do, strongly recommend it. Now I'm going to switch it back to the starting in soon screen because we're going to set up the Zoom meeting. See you soon. Okay. this is with audio now, and what you'll hear now on the Zoom is that the audio is delayed a little bit. The way to do things next, I'm going to turn the audio off on the YouTube again. My sound is now coming entirely through. Oh, you know what? I think that may have actually solved the entire problem. You don't need to do anything with your settings. Don't worry about the audio settings. I just muted my Zoom mic. And that's why you'll have no sound coming from Zoom. Oh, no wonder. So this is actually no problem. Let's get out of here. Share, stop sharing. And I'm going to go stop. I'm going to go back to normal. Yes. So I think we're back now. This all works. So actually all I did, it was very simple. I just muted my own, I muted my own Zoom, and now I'm going to stop my Zoom video. So now everything is on the YouTube stream, and now I can focus right here. I see that some people who came a little bit late, who are trying to figure out exactly how to join this is actually very easy. You don't need to sign in with a G Suite account. All you have to do is go directly to this link right here. You should not chat in YouTube, by the way. If you're joining because you're in the MoMath session, the only comments that I'm able to see are actually the ones that are from the Zoom webinar chat. There's no audio anywhere, some people are saying. There should be audio coming through the YouTube one. Just turn the volume up on your speakers. Actually, it turns out we overcomplicated things. You didn't need to do anything with your Zoom audio settings. All you had to do was just to play it as normal, actually. You only have to play it as normal. Please turn up your sound. Actually, it was easy. You didn't need to adjust your Zoom audio settings at all. By just having your speakers up to normal volume or your headphones in, then you will get all the sound coming from the YouTube. At this point, I want to check in again with the audience that we have from the Zoom webinar. Are you all able to come in now? Yes. So I see that people are getting sound. You should be able to see me talk as well. I would like to get a confirm from the Zoom webinar. If everything is working for you now, please say yes. Great. Okay. I think that means that we are in business. And at this point, we're happy to go ahead and get started. Again, an apology for everyone who's on the YouTube chat. I unfortunately myself am not watching that. Although my understanding is that there are some moderators from our team who are helping to say a few things there. Again, I mentioned this at the beginning. If you came late, the main point of this talk was this is supposed to be a talk that I was supposed to be giving in New York City right now at the National Museum of Mathematics, except that unfortunately I'm not able to go to New York City today. So instead I'm doing this as a live talk to all of you who would have come in person in New York City. And anyone from all over the world who is curious what's going on is welcome to watch as onlookers. Now, I do want to say, I'm very thankful to have this opportunity to work with the Museum of Math. I find that it's a great pleasure to come every single time, physically to their location or remotely like this. I think it's really interesting whenever there are so many people who think that math is interesting, coming to tune in, or usually come in person for an evening of math. Now today, so I see that somebody has said they have some trouble where there's no audio on YouTube. What I would say there is if you're having no audio on YouTube, that's probably just your volume settings on your computer, because YouTube works the way YouTube always works. I also realized that if you can't see or hear anything, that's probably because you might not know where to go. Just a second. Let me put it here. Please go to this spot. So we have this. So if you just go here, then you'll be fine. Yeah, so the entire talk is actually going to go through the YouTube here. So in that case, I think we may as well get started, I think. Okay, great. So I wanted to talk about one of the oldest problems actually in the world. And this old problem in the world is one which people have thought about for thousands of years. Many thousands of years ago, people were, I guess, they were farming. And if you're going to farm, what kind of a shape would be reasonable for your farmland? What do you think? If you were going to make a farm, and actually I want to make this be interactive. So for example, if you are in the National Museum of Mathematics' Zoom webinar chat, please do chat. It's most fun to have an interaction. What kind of shape should you have for your farmland? What do you think? I'm trying to see if the chat is working. By the way, if there are chats, yes, okay, rectangles and squares. I want to say if you're chatting into the YouTube live chat window, unfortunately I'm not watching that, but I will be able to see that the people on the webinar have said rectangles, squares, or circles. You guys have a very interesting imagination. Some part of a sphere. Somebody else has pointed out that, the Earth happens to be a sphere, so we probably need some part of the surface of a sphere. But as you may know, whenever you bake cookies, if you're trying to bake cookies and you try to make circular cookies, it doesn't quite work because there's all this leftover space. And so in that sense, you wouldn't want to make cookies with circles like this. If you were trying to use up all your space, you'd probably try to use something that had straight edges. And so quite likely what you would come to pretty soon is that you should make all of your farmland into something which has straight lines. That seems quite reasonable. So maybe this is how we decide to divide up the farmland. But there's a little bit of a disadvantage to doing something like this. It's so not systematic, and somehow it's hard to tell where is one person's farm, where is the other person's farm. And that's why a lot of people came out to the idea of a rectangle. So now, suppose that you make farmland that's in a rectangle. And suppose somebody tells you they've got a great deal for you. Their great deal is called, you can buy their rectangular farmland. And this rectangular farmland happens to have perimeter 24. 24 watts. I don't know. What's a good thing for 24? I guess it could be a huge farmland if I said 24 miles. Why not? Suppose somebody told you, I have a great piece of farmland for you. I'm sure you'll want to buy it, and then you'll be able to plant lots of crops. And the perimeter of the farmland is 24 miles. Is this a good deal? What do you think? No, not really. Why not? 24 miles is huge. Seems like a good deal. Well, why isn't it a good deal? Let's have some interaction. What do you think? Oh no, what if it's a 12 by 0 rectangle? You could get cheated. And also somebody else has said depending on the price, maybe. But the issue is 24 miles is not the right thing to think about. Because when you plant stuff in a farm, what you're planting is you're planting things in an area, right? The important thing about a farm is how much area you actually have in that farm. It doesn't matter so much how much perimeter your farm has. On the other hand, when you are actually planting crops, those crops are filling up the whole area. And indeed, one of the problems could be you could get cheated very badly with a 24-mile perimeter farm if the 24-mile perimeter farm was just a very, very, very long skinny line. Let's do this. A very, very long skinny line where it's basically just 12 miles long and 0 miles wide. That would be awful. So in that case, this would not be very good. Actually, I see somebody has commented 12 by 12 would be the best. Well, maybe I should have used a different word other than perimeter, because in fact, I will soon want to talk about a different concept anyway than perimeter. But the issue is perimeter is not just the length plus the width. The perimeter of a rectangle would be the length plus the width plus the length again plus the width again. So yes, you mean 6 by 6. That would be somehow the best. The best you could get if I wanted to have a lot of area would have been to put 6 by 6 by 6 by 6, and that would be the best. But now, sometimes you might wonder, could you try to figure out how big farmland is if somebody just told you both the perimeter and the length? And the area? What if somebody told you, hey, there's a piece of farmland, and at some point somebody measured the perimeter of this farmland, and the perimeter of the farmland was equal to 24 miles. And suppose somebody also told you that the area of this farmland, was 32 square miles. If someone told you that, could you figure out what the dimensions of this rectangular farmland are? You would need to figure out how many miles long and how many miles wide. And immediately we see some answers coming out, like 4 times 8 or 8 times 4. Actually, both of those are possible answers. In fact, when I look at these different options, this farmland could have been longer this way and shorter that way, or maybe it could have been turned. Or actually, it could even have been turned like another angle. Basically, all of these 4 by 8 and 8 by 4 are the same size. Now I have a question. How did you guys get that so fast? All I told you is the perimeter and the area. Presumably you did something first with the perimeter, and you said perimeter being 24 is the same thing as the length plus the width being equal to 12. Right? That's what I need to look for. I need to look for 2 numbers, a length and a width, which add to 12. And over here, can someone tell me what the relationship is between the area of a rectangle and the length and the width? This is, I don't want to call it an equation. Equation sounds complicated. But I'm just saying, what do I do with my length and width that is supposed to give me a 32? If I'm hunting for a length and a width that will work, you should multiply them, because the area of a rectangle is the length times the width. So over here, I'm trying to find a way to find out what is L, what is W, so that the length plus the width is 12, and so that the length times the width is 32. And now I want to know, how did you guys get that so fast? I saw some people who said, oh, I know the answer is 4 times 8. I mean 4 and 8. If you were one of those people who answered, or if you're someone else who saw how to do it, could you maybe tell us, how did you get those numbers? What did you do? System of equations. So one way to do this would be if you write a system of equations. There are 2 equations here. We could try to solve, because we have 2 equations and 2 unknowns. Maybe that's one way. But I have a feeling that the people who said 4 by 8 did not use a system of equations where they tried to solve in some way. Somebody else said 6 minus L times 6 plus L equals 32. So that's very interesting. We'll go there. Oh, and somebody else has pointed out, you wouldn't give us a problem that doesn't have integer solutions, so I just tried factors of 32. And that's the answer I wanted to see. You see, because as you all know, if you ever get a problem from a math teacher or a math professor, it has to have a nice answer, right? Or else it wouldn't ask you. In some sense, this is quite true in school. Somehow, if you take a class called Algebra 1 in school, I don't know what the age groups are in the audience, so I'm just going to speak as generally as I can. But Algebra 1 is a class that you learn that's sort of the gateway to all of the mathematics that you eventually have to learn. And not just have to, but it's useful to learn. And now in Algebra 1, which some people take in early high school or late middle school, there are all these questions that look like this, and all of them have nice answers, because somehow it's just not great to give a question with ugly answers. And so when I look at something like this, I see that someone was saying, well, I got to find some nice answers. And 32 is a number that you can factorize. So you try to find some factors of 32, and you tried, for example, yeah, why not? Exactly. You say, okay, is it 1 times 32? No, that wouldn't work, because 1 plus 32 is too big, it's 33. Should I do 2 times 16? I know this is 2. I don't know how to make a 16 with my fingers. But anyway, 2 times 16, well, that won't work. 2 plus 16 is way too big. Then, what if it's 3 times something? Well, that won't work because 32 is not 3 times anything, any whole number. And you eventually get to 4 times 8. And you have just used the tried and true technique called guess and check. And this is indeed how many people, including me, solve these kinds of equations early on when we were learning this in school. Now, there was somebody who said that this is about a system of equations. And if I want to talk about equations, let me now switch to equations where there's only one variable, okay? So let's start with some very, very simple equations. I know that not everyone here has taken algebra. In fact, that's quite normal. Whenever I go to the National Museum of Math, one of the most beautiful things is it's a chance to talk to people who are often very young about concepts of math that are pretty sophisticated. But it's okay. As long as you pay attention and think, it'll be fine. So here's a very simple equation. If x plus 1 equals 3, what is x? Equations are not really rocket science. Somehow, if you have an equation that says x plus 1 equals 3, it just means what could you add 1 to and get 3. And you could do that with guess and check. I see all these 2's coming out. Guess and check works okay when you do equations like this, which are like small numbers. But it's nicer to have a more systematic approach. And the systematic approach I like to use is called, if you beat up both sides of the equation in the same way, it's okay. You get something else which is also a consequence of that equation. And so what will we do? We could try subtracting 1 from both sides. Because if x plus 1 was equal to 3, I can subtract 1 from both sides if I want. And so that tells me that x equals 3 minus 1, which is 2. Strictly speaking, that's not an equivalent equation. But for the purpose of this talk, because I know I have audience members who could be quite young, I won't dwell too hard on that detail. For people who are a little bit more experienced, what I just said is, if I have an x which satisfies this, then that x certainly satisfies this. Because if I've got this equation already true, I can subtract 1 from both sides of it, and it's still going to be true. So that one tells me if I have an x that satisfies this, then the x satisfies this. On the other hand, I don't yet know that this implies that. For that, I'll need to add 1 to both sides. Okay, that was just a comment for people who are into this kind of logic. If you're not into this kind of logic or you haven't thought about that stuff yet, don't worry. What I've done right now is the same as what you're doing in school anyway. So okay, x plus 1 equals 3, x equals 2. Now let's go with something that's a more sophisticated equation. What if I use x squared equals to 4? Can anyone tell me what x's will work for this? If I have x squared equals to 4, 2 works. So indeed, x equals 2 is a solution. Because if I take 2 and I square it, I get 4. But I see there's some more answers too. There are some more answers like x equals minus 2 also is a solution. Okay, so I can do both plus 2 and also minus 2. That's kind of interesting. Does anything else work? I mean, I already found that it's not just one answer. There's already more than one answer. How do I know there aren't any more answers? How do I know it wouldn't be that, for example, if I just keep going long enough and I try some really, really huge number, then finally you square that and you get 4. How do I know that won't happen? Fundamental theorem of algebra. Out comes something which is pretty sophisticated. Another person says, no, it's a degree 2 polynomial, implies 2 roots. Okay, all of these are true. But again, I'm trying to give this talk in a way where if there were people who are on the younger side, we can still explain why it's true. And the fundamental theorem of algebra sounds like, it's pretty fundamental, right? Should be easy. Except that I myself didn't learn the proof of the fundamental theorem of algebra until I went to college. That's not so easy to explain. There's another way to think of it, though. And the other way to think of it, don't have to apologize. You're right. The fundamental theorem of algebra is indeed the hammer that you would hit this with right away. But there's another way to think of it. And I'm just trying to show how with math you can often think about things in different ways. And this will not be a proof, but this would be an explanation that would make some sense. If you have numbers that get bigger and you multiply them by themselves, how does the result compare? Positive numbers. Suppose, for example, I try to multiply 3 times 3, and then I try to multiply 50 billion times 50 billion. How do they compare to each other? Well, yes. Somehow, if you multiply numbers which are bigger, it gets bigger. So somehow, it's like as you're going along, the bigger the number you try, and you multiply it by itself, the bigger the answer you get. So it sort of makes sense that if I start from x equals 0, and I try some numbers which are getting bigger and bigger, at some point I'll have it multiply by itself and get 4. And at some point, and then at that point it's over. It just keeps multiplying and it gets bigger and bigger than 4. So somehow that makes sense that the plus 2 would be the only solution on that side. How about negative numbers? What if I try multiplying minus 1 by minus 1? And then I compare it to minus 2 times minus 2. And then I compare that to minus 50 times minus 50. What happens? What happens when I do that kind of multiplication? Minus 50 times minus 50 is equal to, it's positive. Minus times minus is plus. And this is a pretty big number. Since I'm a perfectionist, I'm going to write the 50 better. Okay. Right, so you multiply them together, it gets bigger, and so that's another reason why it would make sense that somehow as you multiply two really negative numbers, it becomes that you only get 4 once. But that was like a lot of explanation. Okay, now I want to switch gears to something else. In fact, in this talk, we're going to switch gears between a bunch of different problems, and then we'll see that everything was actually related. So the next thing I want to do is I want to talk about what happens when you try to multiply things by each other. And one of the most beautiful types of things to multiply by, to do in multiplication, is to do this kind of a problem. Does anyone know what is 19 times 21? Well, I mean, I could just use a calculator, but that would be no fun. I could do it by hand. I claim that's actually more fun than using a calculator. I see that there are some people here who are pretty quick, who have said that, no, don't just multiply them. I'm going to multiply them anyway so I can compare, all right? 21 times 19, 9 times 1 is 9, 9 times 2 is 18, and then 1 times 1 is 1, 1 times 2 is 2, add together, 9, 9, 3. It looks like some of these people are right with 399. But some of those people who got 399 didn't do it this way. They had a better way. The better way was to say 19. That's equal to 20 minus 1, and that's multiplied by 20 plus 1. Now, we learned in school that whenever I have these kinds of parentheses, there's something called PEMDAS, which is how it's taught in America. But it ultimately means you do the stuff in the parentheses first. So I could say, yes, this is 19 times 21. However, what you often learn in algebra class is that you can multiply these brackets and you can open them up in a different way. And it's not just algebra class. It's like even pre-algebra will often teach that. And so what I'm about to use is I'm about to use the fact that, let me switch to another screen while I draw this, just as an example. If I do something like 1 plus 2 multiplied by, let's say 3 plus 4. What is that? I could do it where I just multiply. But what I would rather do is I'd like to think of it as like this kind of a square opening up. Not a square, like a rectangle. This is like 1, this is like 2, this is like 3 and 4. Let's pretend these were right. 3 and 4, 1 and 2. So if you can see what I'm doing, I'm basically proving to you this thing called the distributive property. That if I wanted to know the area in my rectangular plot of land, which happens to be divided into 4 subplots, I could just add up each of those plots. Like I could take the 1 times 3. Oh, I've got colors. I could take the 1 times 3 and add it to the 1 times 4. And you see where this is going. Again, if you've learned this before, I apologize, but I want to make sure I can bring along everyone in this diverse audience to learn at the same time. And then I also have a 2 times 3 for this piece. 2 times 3. And the last part is 2 times 4. And fortunately, I had just enough colors to pull this off. So as you can see, I could just think of it as dividing up plots of land, and that's why the distributive property works. Pull it back to the other problem. So here, if I try to do the same thing, it's nice. This is just going to be 20 times 20, which is nice. We like multiplying 20 by 20. But then I'll write the next things with some other color, plus 20 times 1. And then I have minus, let's do this. I'll call it plus negative 1 times 20, plus negative 1 times 1. The last part, maybe I should put in the normal color, plus negative 1 times 1. And so if I put everything together, what I get is I get the middle terms canceling, and I just get 20 squared minus 1 squared. And that's equal to 400 minus 1. Which is equal to 399. And so that was nice. So that's a very, very fast way of multiplying these kinds of things together. Okay. But now the reason this is useful to talk about is because the next thing I want to hit is another piece that's in quadratic equations. Actually, we're just talking through quadratic equations, but we're doing it in a way which is going to soon give a different angle. So in quadratic equations, sometimes you find yourself wondering what happens if you had an x. But suppose I had an equation which was like x minus 3 times x minus 7 equals to 0. Now we go to quadratic equations. And now I've written this. If somebody gave me this equation and said, find all the x's that solve this, what would you do? Suppose I already saw the equation in this way, and I'm supposed to figure out what are all of the x's that make this equation true. Well, I see that 3 would work. If I put 3 here, 3 minus 3, that's 0. So I have 0 times, well, 0 times anything is 0. Done. Similarly, if I had x equals 7, which is also what I see, throw the 7 here. 7 minus 7 is 0. Anything times this 0 is 0. Done. Actually, those are all the solutions. And the reason why is because if I have two things multiplying by each other, and these two things happen to be multiplying together to make 0, that happens precisely when we have one of them is 0 or the other is 0 or both. I see somebody said, if x minus y equals to 5, are we able to get one correct answer? I'm not entirely sure. I think maybe it could be that I can't read because my vision is not that great, but I saw someone asking about x minus y equals to 5. So we don't yet have a y here. So it could just be that I can't read and you didn't write a y. But I can look at this one. It's even closer. So maybe you did write y. I'm not really sure about that. And I see some people here talking about integral domains and fields. You're right. But as you can see from the way I'm doing this talk, I've actually been really trying to make it as accessible to people who are young as possible. For one very important reason. It's that quadratic equations are usually thought of as complicated things. They are often thought of as hard to solve. And that's why you kind of work your way up to quadratic equations. My goal here is to be able to talk about quadratic equations to people who are like really young, who just kind of know how to multiply some numbers together, because it turns out that's all you need to do. Okay. And so the key here is if you know how to multiply some numbers together, you have noticed that somehow, some people know where I'm going. It's like if I'm multiplying numbers together and it's 0, there's only one way to do it. It's if you used 0 for one of the numbers. And you know that if you've just been doing multiplication. You don't need any crazy math to know that. So here, the solutions are precisely when you have x minus 3 equals to 0 or x minus 7 is equal to 0. Those are the only two ways. And that's because I need to have two numbers that multiply to 0. And bam, there we got it. Because this is the kind of equation we saw before. X minus 3 equals to 0. Oh, come on. It's clear there's only one x that works there. It's x equals 3. X minus 3 equals to 0 is a very easy equation to solve. X minus 7 equals to 0 looks like it's going to run into my head. So I guess I'll run the other way up on the screen. And that will be x equals 7. Boom, we're done. And now there's something very important. What we have just learned is something called the factoring technique in quadratic equations, but I didn't have to call it that. It's like if somebody gave you an equation and it already looked like this, you're done. You just have to solve it by looking at those numbers that are after the minus signs. So now, I want to talk about another equation. I want to talk about an equation which looks like this. It's going to look a little bit different. It's already going to be called x squared minus 10x plus 21 equals to 0. What can we do here? Now I want to know, what are the x's that could possibly make this could possibly make this equation equal to 0? Wow, some people are so fast. You managed to see that 7 works? How are you so fast? Looks like some people figured out that x equals 3 and x equals 7 works. Those look kind of familiar. And why is that? There's a reason behind all of my madness. There's a reason why I give all of these problems in this way. It's because actually this is the same equation that we just did. And that's because it turns out that if you go and look at the equation we just had, this x minus 3x minus 7, what would happen if you just tried to expand this out and find out what that left-hand side is? You know, we already know that if I'm multiplying something minus something times something minus something, you can use the distributive rule. And so, in fact, this is exactly equal to, if I multiply, I get x times x. We usually write that as x squared. That's from those two. I get an x times minus 7, which is minus 7x. And then I get a minus 3 times x. And I get a minus 3 times minus 7. So it's like plus negative 3 times negative 7 is 21. Are people with me? That's just like, it just so happens to be this side. Which is perfect, because this is exactly the equation I just gave you. The equation I just gave you was x squared minus 10x plus 21. It's the same. It's the same. So this that we just did, where the solutions are 3 and 7, is exactly the same as this. So we have now sped through our Algebra 1 lesson, and now we have learned that there's one way to solve this. It is if, there's a big if here, if you can write the left-hand side part, well, let's draw a box around it. If you can write the box in the form where the form looks like this. It's like x minus something times x minus something. Let's not write an equal sign. I'll write the word as. If you could do that, where you put two things here, then what we just saw before is that actually all of the solutions are just these two things in these like pink boxes. Then all the solutions are whatever is in these pink boxes. Are people still with me? I want to do a quick double check because, again, I need to get some feedback. That's why I love doing things as interactively as possible. I'm particularly interested in, like, if you happen to be a parent who's watching this with a younger, student, I'm actually quite curious whether, like, even like pretty precocious elementary schoolers are like, that's not a big deal, because we're basically doing something that's usually taught in America to early high school or late middle school students, but we're not using much of anything. We were just thinking about land, and then after thinking about land, we thought about multiplying and expanding these brackets, and then we saw stuff like this, which has an x squared. But if you're so lucky as to be able to write it in this form, where it's like x minus something times x minus something, bang, you're over. It's over. Those are the solutions, whatever goes there, for the same reason as when it was 3 and 7. Because if I have x minus something times x minus something, these things are supposed to be, one of them is supposed to be 0, and that's it. So then the game becomes, what does it mean to be able to get those? And this is what we did in algebra class. So now this is getting to maybe my own experience. When I learned Algebra 1 for the first time, we had textbooks. And the textbook said, if you ever see something like that, if you would be so lucky as to go and find some numbers to put there so that multiplying this gave you that, you'd be in good shape. By the way, the textbooks usually had it with writing plus signs there. But you see, I like minus signs because then I'll just be able to say that's the answer. Whatever I put in those boxes is the answer. So now, what does it mean to be able to find this? to be able to find this, what I mean is the x squared part comes already. That's the x times x. What do these two pink boxes have to do with the 21? Let's start with that. How would you make that if happen? To make that if happen, I'll write this happens when, maybe I'll say this happens if, let's do that. This will happen if I'm lucky. Whoa, we have some interesting chat at this point. I would like to request that if you are in the Museum of Math's Zoom chat, please don't pollute the chat, because this is the one that we're using. So somehow they're factors of 21. So I need these two things to multiply together to give me the positive 21, right? Oh, wow, somebody even figured out how to write boxes. This happens if I need two things to happen. There's an and. I need the two boxes. The two boxes, by the way, represent potentially different numbers. They need to multiply to 21 because they're both with minus signs. And what else do I need? Oh, I see somebody else said the pink boxes have to also add to 10, to positive 10. They have to add to positive 10 because of the fact that I will make the minus 10x by having x times the minus 1 pink box and the minus the other pink box times the x. So that's all I need. Does anyone know any two numbers that happen to multiply to 21 and add to 10? Well, that's not so bad. Multiplying to 21 and adding to 10, how do you do this? Well, what we all learned when I was doing math in school before was that you just go back to the tried and true of guess and check. You factorize the 21, right? So there's all these problems whenever you're solving these things where you go and try to find a way to factorize out the 21. And after you factorize out the 21, then you're in good shape because that's like 3 times 7. Oh, it works. And you're done. So indeed, I can do that with 3 and 7 because 3 times 7 is 21 and 3 plus 7 is 10. So now at this point, you've learned how to solve quadratic equations. If you have something that looks like this, all you have to do is see if you can figure out if there are two numbers which multiply to that piece and which add to minus of that piece, so just the 10. If you're so lucky as to find those two numbers, boom, then those are the answers, 3 and 7. Okay. So now I want to go and talk about a more complicated equation. Not more complicated, it's just got bigger numbers. X squared minus 20x plus 72 equals to 0. Well, now we just have to do the same thing, right? I would be done if I just find two pink numbers. I'm done if I can find two pink numbers, and those two pink numbers have to satisfy something and something. I'll write the and out here. The two pink numbers have to multiply to be 72, and they have to add to, if you remember how this is all going, whenever I was going to factorize it, then these two things have to add to the 20. And just to remind people why that is, that's because we have x minus something times x minus something. And these somethings need to be such that if I went to multiply this stuff apart, it would make that. Now the interesting thing is I see that the chat has quieted down. Because, you know, our audience here is pretty sharp, so somehow, usually the answer comes out pretty quickly. But somehow the chat seems quiet. And I think it's because 72 has a lot of factors, so it takes a long time to try this, right? Like you have to go and say, does 1 times 72 work? No. Does 2 times 36 work? No. Looks like Yevgeny thinks that minus 2 times the square root of 7 plus 5 is a good choice. How'd you come to that by guess and check? There are no whole number factors. This is an example of a time-wasting problem on the test. So this is like the worst possible problem to run into on a test when you're taking algebra in school. Because you look at this and you say, oh, 72. I just need to go and somehow factorize out the 72 or find Wolfram alpha, and please don't cheat when you're taking tests. But you know, like I look at 72 and I say it'll take me forever, but I'll try all of them. And after you tried all the factors, you say, none of them worked. Oh no. And when none of them worked, what do you have to do? Well, that's why we had something in school. It has a name, something that everyone memorizes all over the world. It's called the, does anyone know what I'm about to deploy, what I'm about to use? You have a very special way to know what are the solutions to any quadratic equation at all. It even has a song that goes with it. It's called the quadratic formula. Now, I'm not very good at singing. I'll try to do my best. So in America, the way people memorize this formula is that there's actually a song. The song goes to the tune of Pop Goes the Weasel. This is a YouTube video which has like 1 million views. It's amazing. So let me try to go. So the song goes, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I don't know how many people here have had to learn that song. But this is a song which somehow helps everyone remember the way to solve quadratic equations. And if you look at this, if you've never learned about quadratic equations before, this looks like a mess. And it is a mess. But the interesting thing is you don't need to do this. So we're not going to need to do this. I came upon this idea that I'm about to tell you about because I was trying to find a way to help more people in America and in the whole world to understand quadratic equations. And I know that this quadratic formula is the first point in math where a lot of people, maybe even the majority of people, just memorize something, possibly even with just a song, with like someone says, lol, does that actually help? I don't know. I mean, somehow, what else will you do, right? If you don't use the song, there are other people who did what I did, which is just like commit it to memory, just memorize it, okay? And unfortunately, that's sad. I mean, math is not about memorizing anything. The whole point of math is to be able to think through everything that we're doing. And so, I came up with a different thing that you could do. Because whenever I try to teach math, I always try to say, is there any other way? Is there any other way? That's actually how I grew up doing math. I always was interested in other ways of solving problems. On the one hand, it helps you to also be more accurate, because if you do the same problem in 2 ways, then, it's probably right. On the other hand, it's also beautiful. So, let's go back to this problem. Let's suppose I want to find 2 numbers that multiply to 72 and add to 20. Here's where everyone, even including me, everyone was starting from the wrong point. Why do you want to factorize the 72? Oh, indeed, somebody has said you can use a method called completing the square. In fact, what I'm going to tell you about is mathematically the same calculations as in completing the square, but what I know from having taught students, especially even like general public students, about quadratic equations, is that completing the square is very difficult to get your head around the first time you learn about all of these x's. I mean, like this kind of an expression, if you're new to algebra, this is a mess to look at. So I don't want to say completing the square. Oh, wow. So somebody here who is, maybe this person has experience teaching, saying students hate completing the square. The main problem is, first of all, I want to say, I also think completing the square is beautiful. There's beauty in that one too. But the problem is if you're just brand new to all this stuff, it can be actually a lot to stomach. So I'm going to go back to just talking about find 2 numbers that multiply to something and add to something. Completing the square gets confusing at times too. That's true. But you see, I claim that this problem about product and sum is as fundamental as the perimeter and area problem that we opened with. In fact, this problem of finding 2 numbers that multiply to something and add to something is as old as humanity making rectangular fields and wondering about them. Thousands of years old. Let me show you a method which I had never seen in any textbook. I've actually never seen this in any textbook anywhere in the world. And that's after me putting this thing out and the New York Times covered it. There is no textbook I've ever seen that talks through exactly what I'm about to do. And we should change that. So again, what we said here was, if we're so lucky, this is an important if, okay? I don't know for sure that I'm going to be so lucky. But if you could find 2 numbers so that I get a product. Actually, I'm going to write the product on the second line. A product of 72 and a sum of 20, then those are all the solutions. Okay, so now here's what I'll do. Let's not start with the product. You know, everyone was factoring. Factoring is unmultiplying. Everyone was saying, can I unmultiply the 72? No. Different way. Let's start from this sum. Let's unadd. Now, a lot of people are used to thinking of factoring as something that they would do in school because, you know, it's a real problem. If someone said, find two numbers that multiply to 91, you know, everyone would be like, oh, come on, there are no such things. It's 1 times 91 because 91's prime, right? Doesn't everyone know that 91 is a prime number? It looks so prime. Oh, oops, it's not. 91 is actually, what is it? It's like 7 times 13, I think. Yeah, thank you very much. So that's really, really frustrating. But when we talk about unsumming, everyone's like, well, that's easy. Unsumming, if I want to find two numbers that add to 20, here's one way, 10 plus 10. Here's another way, 9 plus 11. Here's another way, 9.5 plus 10.5. Do you see what I'm doing? I'm saying that if I find two numbers whose average is 10, automatically their sum is 21. Like if I found a number like, I don't know, 0 and 20. Those are also numbers that average to 10, and then their sum is 20. I drew an arrow here. The arrow is the direction of logic. So, if I can find some number, I don't know what this number is called. Maybe I'll call this number a u. If I can find a u. So that the two numbers, so I'll just write, if I can find a u, so that the two numbers 10 minus u and 10 plus u work, then I'll be done. See, what I said here by work, what do I mean by work? See, a u represents like how far away we're moving from the average. Because if I can just find two numbers who average to 10, automatically I will in fact get the first thing to be true. This is actually the interesting observation, is that somehow I'm wondering, can I find two numbers? I translate that into saying, now I'm wondering, if only I could find this one, this u, then actually 10 minus it and 10 plus it would work. And I would be able to have two numbers which add to 20. For free. That one's for free. Oh no, I've got the other one. What does work mean? Well, work, the statement will work means, what will give me that if, is I just need that the 10 minus u times the 10 plus u has to multiply to 72. Does that make sense to people? I see somebody is saying that there is a problem with the Zoom audio. Okay. Let me actually say, I see that somebody in the Zoom meeting has had an issue. I'm going to type a message to them, which is just, please watch here. Okay, that's right. And it's because somehow, it's because it's one of these funny things. I can't just go and talk to them here and say, oh, just join this YouTube channel and you'll be fine, because they're not on the YouTube channel anyway. But anyway, hopefully they'll be able to join us soon. Anyway, so back to this. It's like, if only I could find a u so that this times this was 72, I'm done. I managed to find two numbers which add to 20 and also multiply to 72. So in that case, how do I do that? Oh, but this is nice. We saw something like this before. I also talked about like 20 minus 1 times 20 plus 1. This is this thing called the difference of squares. But even if you didn't know that, let's just open this up. 10 minus u times 10 plus u, that's just 10 times 10. 10 times 10, which is 10 squared, which is 100. And then plus 10u minus 10u, minus u squared. I'm wondering, could I make that equal to 72? Now I have to duck because my writing got too close to my head. You see, so what I'm saying is that I'm looking to know, I wonder if there's a u so that 10 minus u and 10 plus u work. That would be great. Work. Work means multiply to 72 because they automatically add to 20. Multiply them. Let's find out. And the beautiful thing is the middle terms cancel. Plus 10u and minus 10u are the same. And so it turns out that if only I could have, I'm drawing all the arrows to say if I have this, then I have all of these and I'm done. If only I could have a u, so that 100 minus u squared was 72, could this be done? Can I find a u to make this happen? Well, actually, this turns into an easy equation now. Although this is also a quadratic equation, this is actually a lot easier to solve. Can anyone see what I might want to choose for u? And I'm actually really interested in, if there are, parents are here with younger students, the beautiful thing here is actually younger students who know what a square root is, or know the concept of find a number which multiplies by itself to make something, boom, it works. So this is actually not very hard. 100 minus u squared equals 72. I'm just wondering, is there a way for me to stick a u here so that 100 minus this thing is 72? Well, we've solved that kind of equation before, but you don't have to think about equations. It's like I need to have 100 minus something is 72. Well, that something better be 28, because that's the difference between 100 and 72. So I'd be in good shape if only I could find a u squared, which is 28. If I have this, then I have this, and it keeps going up. And people say, just use the square root of 28. Actually, I'm done by just choosing u to be the square root of 28. Now, I could simplify that. Some people called that 2 times square root of 7, but that's not very important. At this point, we just know I could get something. And the important thing is that's not a whole number, right? Now, you might wonder why I didn't write the minus in front. How about plus or minus? Well, my flow of logic is it just goes up. It's like if I just have this thing, then I can go and unroll every step. And if I unroll every step, I find out that using u to be the square root of 28 is good. It will give me these two numbers that work. In fact, those two numbers will be 10 minus the square root of 28 and 10 plus the square root of 28. That's a very long comma. Let me draw it again better. And those definitely are all the solutions. The flow of the logic is, oh yes, there was a question, is this recorded? To be perfectly honest, the answer is yes, this is actually being recorded in my studio here. I have all the equipment recording this all at the same time. So that will be a question of if we decide that we want to release afterwards. Maybe we can talk to the Museum of Math about that if you're curious about this. But in any case, to go back to this, it's that somehow I've just found out that if I choose u to be the square root of 28, okay, it squares to 28. Okay, 100 minus its square root is 72. That's the same as this thing, which is the same as that thing. So I've just found out that these two numbers multiply together to 72. I'm done! And that's actually the solutions to this quadratic equation. So it turns out that you can actually solve all of these quadratic equations. Rolling back one. You can solve all of these quadratic equations without guessing at all. If you look back at this, it's like normally the way we think about this is we try to factorize the 72. And everyone all around the world learns, actually me too, when we did Algebra 1 from every single textbook. When you see this, the way to do it is to try to prime factorize the 72 and guess and check. This is not any teacher's fault. This is in every single textbook all around the world. And actually those textbooks all say, well, if it doesn't work, then there's completing the square, which is actually mathematically very similar to what we just did. And there's also this quadratic formula. But the surprising thing is, if you just like, instead of trying to break apart the 72, you try to break apart the 20, break apart the sum, then you actually don't have to memorize anything. And in fact, this problem just becomes one where you've unpacked each of those steps. And in fact, you can reason through every single one of those steps. What's the point? Thanks for asking. Actually, this is where we want to start to get some of this discussion. Quadratic formula is so much quicker. You're right. It is so much quicker to memorize that negative b plus or minus the square root of b squared minus 4ac all over 2a is always the solution. But then the question becomes, what is our goal in teaching math in the first place? Maybe I might have a different opinion than, I'm not the same as everyone else. My opinion is that one of the main purposes of learning how to do math is to learn how to think. It's nice to be able to solve equations, but the average person will need to actually solve a quadratic equation in their real life. After graduating college, the average person will need to solve a quadratic equation in their real life 0 times. I said the average person. There are, of course, there are people who are watching this live stream who are scientists, engineers, and you may find yourself solving quadratic equations because maybe it's directly related to work that you're doing. I mean, I even will see it in the work I'm doing as a mathematics researcher. But if we're thinking about what the general public, like the median person, like the average person in the whole society, whoa, we're thinking about the same thing at the same time. The median person, like somehow, like somebody who's like just in the middle of society, what should they be getting out of an algebra class? And so my personal opinion is it's fine for them to also learn quick ways to solve problems, like by memorizing this, by singing a song that has the same tune as Pop Goes the Weasel. That's fine. But what would be much more interesting is if that person, if you stopped them on the street and said, hey, why is that true? If that person could actually go and explain to you why that's true. Oh, interesting. I have a question about, like, would it always be half of the number you add to? Yes, thanks for thinking. You see, the point of why I wanted to talk through this is because you can pick apart the math inside it, right? Which you can also do with completing the square, but this has no, like, symbolic mess. So it's like, if I wanted to find this relationship between the 20 and the 10, you see, my arrow here said, if I can find a number so that two numbers who average to 10 work, then they'll sum to 20. And that's because of the relationship between the average of two things and their sum. The sum is always twice the average of the two things. Your 6th grader wants to know, will you send us the URL for Pop Goes the Weasel? Oh, we can do that. Actually, to do that, honestly, you just have to search YouTube for quadratic formula song. Although, I should add that, in fact, I was actually involved in helping to create another music video about the quadratic formula. And there's it's a rap music video, and that's also on the internet now too. I'll be happy to share that one with you. The idea is that somehow there are some people in the world who think that Pop Goes the Weasel is like the most exciting music in the world. Yeah, okay, there are. But there are also some people who maybe will have something which would like something more interesting. So maybe if we have a way of communicating with you afterwards, I'll be happy to send you both of those links. She thinks she found it. It's not very hard to find. In fact, actually, the fact that there are so many different ways that people have been trying to memorize the quadratic formula shows that unfortunately, a lot of people are not understanding why it's true. You see, the main problem is that if the game becomes, let me just memorize it, then unfortunately you've sort of missed the point of the math. Unless you are in such a situation that you need to someday solve quadratic equations all day, and it would be easier just to plug them into something. Just to give you an example, like what am I doing right now? Actually, some of you may know, right now I'm actually working on an app to help to combat coronavirus. In fact, that app was supposed to release like today, except that I stopped to do this live stream with you guys, and after this live stream we'll go back to finishing up the website, and then hopefully this app will hit the world within about 12 hours. But I'm just explaining to you, like, this is what I do myself. And deep inside that, I was just working with something called Fourier analysis. There was something called the Fourier transform. And me personally, I don't memorize these things. Actually, there might be some engineers in this audience who use Fourier transforms for signal processing. And, what app? You'll hear about this soon, I think. This might be a pretty big deal. But in any case, it's like somehow the Fourier transform is something which has a very complicated formula unless you understand what it is. And it has e's, pi's, and i's in it. But what I'm trying to communicate is, yes, if I knew it off the top of my head, no problem, I would have been faster at writing it down. But ultimately, to make this app work, I needed to pick apart that to do something else that was inside it. And that was by understanding ultimately what everything was, I was able to do so. And so my hope, by giving this talk about quadratic equations, yes, thank you very much for saying intuition matters in math. My opinion is that if you are the kind of person who watches the Museum of Math's talks, you probably are also caught by this, you've also caught this bug that math is not about memorizing. Math is about trying to figure out why things work and someday looking at it from a different angle and picking it apart. And so I'm not saying that this is the most efficient way to solve quadratics. In fact, it's not. However, what I've learned after coming up with this particular presentation, I've learned that there have been quite a few adults who are maybe not the kind of people who themselves would frequent math museums, so they're not like math aficionados, who have said, oh, once you explain it this way, I actually understand how to solve these equations. And so the point is, that's actually what my goal is. It's slower. But actually, if you're trying to understand how everything fits together, you can see it. Whereas if somebody said, it's this, everyone, it's a little bit hard to see right through it. Again, everything has its value. I use this too. I use this too whenever I need to do something fast. I just wanted to show a new way of looking at something that's different. Where new, what I mean by new, is to virtually everyone in the world. We're all used to learning math, where you pick apart the 72 first and you factorize. And then you go and hunt for things that, by guess and check, add to 20. And the idea here is, oh, you can just break apart the 20 first. And then you want to find this u. And when you want to find the u, it actually boils down to just finding out what squares to something else. And this actually works on every quadratic equation. If you're curious, I can also share another YouTube link. In fact, I have a 1-hour video. It's actually on my YouTube channel, this thing that's hosting these live streams, including the one you're seeing now. There is a recorded video on this channel, which for 1 hour just talks all the way through here. You just blew my mom's mind. Let me tell you, I blew my own mind when I saw this. Okay? I came up with this because I was coming up with ways to teach people math in more creative ways. And normally I work with university students. But I started working with younger and younger students, and that took me eventually to this. And I used the same technique of thinking, are there other ways? Are there other ways? And when I saw this, I basically almost fell out of my chair because I should have seen everything that's been out there before. My job is to teach math, so there should not be something that is like that new to me. However, over here, you can just solve every quadratic equation just by doing this. Okay, great. But now what I want to tell you is it's not new at all. In fact, the technique I just showed you is about 3,000 years old. Now that is even more mind-blowing. So after I thought of this, I then went and did a lot of looking into mathematics history. I wanted to know what everyone did, like Greeks, Arabs. There was a Persian mathematician named Al-Khwarizmi. He's the one who came up with completing the square. There were Indian mathematicians. There were mathematicians from all different cultures. And it turns out the Babylonians did it this way. The Babylonians, by the way, are about 3,000 years before now. And in fact, the Babylonians, if they ever had to solve equations that were like find two numbers that multiply to, see what the thing was? Find two numbers that multiply to, oh, let's make something that's complicated. Multiply to 899. And suppose, maybe they didn't call it perimeter. Let's just call it length plus width. They wanted to find a particular field where the length plus the width equals 60. If the Babylonians were trying to solve this, they would all do it in the way that I just talked about. They wouldn't do this by trying to factorize the 899. In fact, they would just say, all right, if I'm looking for two numbers that add up to 60, let's all do this together. How could I get that? I could get two numbers that add to 60 if I just use two numbers whose average is how much? I'd like to find two numbers whose sum is 60. 30, thank you very much, half of 60, right? It's like if I have two numbers whose average is 30, 30 is here. If the average is 30, the sum is always going to be twice of it, right? The sum is going to be twice the average because there's two numbers. So the question is there a u? So that 30 minus the u and 30 plus the u work. Could I make it so that 30 minus u times 30 plus u work? Work, what does work mean? They already will add up to 60. Work means multiply to 899. Is this possible? Now it looks like I'm drawing from top to bottom. But it's okay. The beautiful thing about math is it's logic. As long as you trace the direction of logic, you're fine. I need 30 minus u times 30 plus u. Does anyone know what happens if you try to expand that apart? Well, it's the same thing again. I always have something minus something, and the same first thing plus the same second thing. Will my notes be available after this session is over? I'm going to break something to you. Actually, this entire session was done by improv. So there are no notes. In fact, what I've been doing is I have some ideas in my head, I've been looking at the entire chat, and I've been improvising everything as we go, so that while I look at the clock, we're going to get to the punchline before 8 o'clock. So there are actually no notes. On the other hand, I don't know, it doesn't look like the Zoom meeting's being recorded, but I will say that I actually have a complete recording of everything that's going on right now. Not your chat, but I have a complete recording of every single thing of me talking and on this thing on this green whiteboard here. green whiteboard doesn't make sense. But already, people have solved the whole thing. Look, because if I have 30 minus u times 30 plus u, that's easy. It's easy because like 30 times 30 is 30 squared, which is 900. And again, the middle terms cancel. That's why this is so nice. 30 times plus u is plus 30u. And minus u times 30 is minus 30u. Zoom is recording. Zoom says it's recording including the chat. Well, in that case, you can also get it. Oh, wait, but the Zoom won't help because this video is not in Zoom. But actually, the YouTube thing, usually the YouTube automatically records too. Don't worry, we'll figure it out. We'll figure it out one way or the other because we have all the footage. And lastly, minus u times plus u is minus u squared. That's equal to 899. Sorry, if I can make that equal to 899, then I'm here. Okay, the pinkish stuff cancels. They're the opposite of each other. So now I just need to know, is there any way to make 900 minus u squared to be equal to 899? Notice my direction of logic is top to bottom, meaning if I could find you a u that works with this, it will work for this, it will work for this. It will give me a 30 minus u and 30 plus u, which give me both of those. Anyone know a u to use? I guess I already see people have put 1. Just use 1. That works, because 900 minus 1 is 899. I can do this using u equals 1. You may notice, like, you're used to people writing plus or minus 1, and that's if I wanted to write these things called if and only if. If I wanted to say, from here, then that's true, then that's true, then that's true, then I would indeed need a plus or minus 1. But for the purpose of me just finding a u to use, I just need to go down. I just need that there was a u, that's called 1, which makes 900 minus u squared, 899. Hooray, it does. Then it's like, well, then this part's 899, because I just add and subtract the same thing in the middle. And the left side is the same as this anyway, so then, of course, with u equals 1, this times this is 899. And so the two answers are 29 and 31 work. And this is how the Babylonians solved this kind of problem. How do we know? Well, the Babylonians wrote things in clay tablets. They use some, what's it called, like a stylus to draw like these triangles in clay tablets. And also, there's also been written words by Diophantus. Diophantus was a Greek. He was from about 2,000 years ago, and he also wrote down this idea. So this idea is like ancient history. Then the deep question becomes, how come it was so standard before, and then like 2,000 or 3,000 years later, we don't see it in any of the textbooks, standard textbooks. We don't see this method as solving a complete quadratic equation in any of the standard textbooks. And so much so that we even get interesting comments like people saying, wow, that's mind-blowing. So first of all, I need to emphasize, if you look in textbooks, you can find this piece. It's a historical piece. But somehow the connection of saying, here's a historical piece, and now let's use it to go and solve a general quadratic equation, which is what I just showed you, that's just not in our standard textbooks. It should be. And now let's answer the deep question. Why did the Babylonians think that this was so natural? There's a really good reason. Does anyone know how the Babylonians kept track of numbers? Does anyone know what number system they used? What do I mean by that? Here's the number system that we use today. The number system that we use today is we write 0, then we write 1, then we write 2, then we write 9, and then we write 10. We write a 2-digit number because we only have 10 symbols, 0, 1, 2, 3, up to 9. We have only 10 symbols, and then after that we use the next place value. Okay, there's 1, 0, and then it becomes 1, 1. This is today. Babylonians, I cannot write Babylonian, by the way. I also believe they hadn't invented 0 yet. But somehow, Babylonians, they had like 59 digits, 59 non-zero digits. So their numbers would be like weird squiggles until eventually you get 2 weird squiggles. But the number of these would be 60. So they would have like base 60. Again, I'm being a bit, that's not quite right because they didn't have 0, okay? They didn't quite have 0. But they basically had a base 60 means that once you get to 60, that's like the next hour. Actually, you're used to base 60. Base 60 is called time. Like, somebody might tell you, this is going to be for an hour and 30 minutes. You have just used base 60. Because base 60 is where you say, I'll just keep counting up until I get to 60, and 60 is a special thing. Actually, I could say hours, minutes, and seconds. That works too, right? And with our time type, you're right. Our time type cycles, we can use base 10 digits to represent our time. But I want to explain to even young people this concept of base 60. It's like seconds, minutes, and hours. So if somebody told you it's 3 hours, 15 minutes, and 12 seconds, you're always thinking of putting things together in multiples of 60, where every minute is 60 seconds, and every hour is 60 minutes. We don't go any further beyond that, though. Okay, so they were using base 60. Now, when you think back to how we did this, in the beginning I told people, can you find me two numbers that multiply to 21? Everyone said, oh, I know how to do that. That's easy, because people here have memorized the multiplication table. So people here in this particular chat have memorized that there happens to be a 21 right here. Do you know what I mean? It's like somehow when we talk about multiplication and you say 21, we've done these problems so many times that we say, it's that one over there. That's the 3 times 7. Okay? So we're used to being able to pick apart, factorize a number by just thinking, where in that multiplication table do I ever see 49? That's 7 times 7. Now, suppose you're a Babylonian. What does your multiplication table look like? If you're a Babylonian, your multiplication table is kind of big, because you don't have a 2-digit number until you get to 60. So there's squiggle here, which corresponds to the 1, squiggle here, which corresponds to the 2, squiggle here, which corresponds to 3. Again, I can't write in cuneiform. I can't write in their language. All these weird squiggles, 4, 5. How many squiggles are there across the top? Does anyone know? How many squiggles would you have in the Babylonian multiplication table? I'll write that number of how many in our normal way of writing numbers. 60. If you imagine a 1 to 10 by 1 to 10, or a 0 to 9 by 0 to 9, indeed, some people say 59, some people say 60. I'll say about 60, okay? It's big enough, about 60. And that you should think of in elementary school, we see all these 10 times 10 multiplication tables. In ancient Babylon, it would be 60 times 60 multiplication tables. So, here's a question. How long do you think it takes to memorize the 60 by 60 multiplication table, where you need to know every single one of them? I don't think I personally would even be able to do it. It's not a question of how long would it take. Okay, maybe if my entire job was called just memorize the multiplication table, maybe I could do it, but it's horrible. It's too long, at least 5 minutes. You guys are so funny. Yes, it would take me at least 5 minutes to memorize this table. That is correct. Somebody said there are 3,600 numbers here. Actually, that's true. And you can also save a factor of 2. Actually, my angles are off only because this is flipped. Just so you know, my screen is flipped. So sometimes I move in the wrong angle. But anyway, it's which way does that go? This way. No, the other way. This way. Good. There's some symmetry here. Wow. Somebody has made a 50 by 50 multiplication table before. Look, it's symmetric. So whatever is here is the same as whatever is here. Right? So in some sense, I can save a factor of 2. So someone's fast in 1 second. But, save a factor of 2. So up here, there's half of 3,600. That's about 1,800. That's about 2,000 things to memorize. Horrible. So actually, for a Babylonian, the idea of factorization is not easy. Factorization, meaning find two numbers that multiply to something, is not easy, because they can't hold the whole thing in their head. They won't be able to say, oh, I know, 899 is right there. How would you know? On the other hand, though, they had another way, a very ingenious way of multiplying numbers. And that takes me back to the beginning of this story. If you ask somebody, an ancient Babylonian, to go and multiply two numbers, let's pretend the two numbers they want to multiply are 21 times 25. What would they do? Well, they wouldn't do it. By the way, the 21 would be like blob. 25 would be blob. Each of those is an individual symbol. Why didn't the Romans use this method? Well, Romans had an even worse way of writing numbers. They used these things called Roman numerals. So those are very hard to do arithmetic with, actually. Yes, thank you. Somebody has said factoring in Roman numerals is much worse than factoring in base 60. This base idea is actually pretty darn good. Like, I mean, come on. Does anyone want to factorize the number MCMV III? No! What are you going to do with that? What is that anyway? 1908. That's what that says. Okay, anyway, you get the idea. But if you were trying to do 21 times 25, Babylonians had a method. They used 23 minus 2 times 23 plus 2, and that's equal to 23 squared minus 2 squared. I won't write it out anymore. We used to, earlier in this talk, we wrote like plus and minus some stuff. But here you have this. So 23 squared minus 2 squared, that's all you need to do. You only need to do subtraction. And in fact, Babylonians had tables of squares. You could actually go and find that they had some tables, and the tables told you the squares. They would tell you the squares, 1 squared, 2 squared, 3 squared, 4 squared. You could look them up. This is a cool trick because it actually, look, there's 2,000 numbers here. But there's another way. You could just make a list of squares. The list of squares is called 1, 4, 9, 16, 25, all the way down to whatever is 60 times 60, 3,600. But they wouldn't write it with these like 2-digit numbers. They wouldn't write it with this like numbers in base 10. They just had blah, 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 blah. And all those blobs would be the squares. So if you want to do 21 times 25, just go look for the 23 squared and the 2 squared and subtract them. And if you want to do things which aren't both of the same evenness or the same oddness, you can either choose to add one more number, or you can choose to use half integers. Both of those are fine. But I'm just showing you that this is actually more efficient. If you had to write down a 3,600 number multiplication table, that takes a lot of space. If you just write down a list of squares and you do your multiplication by subtracting the squares, you're done. Like 21 times 25 is the average squared minus the gap between the number and the average. And that might be why they thought that was the most natural way to go and solve the problem of find two numbers that multiply to 899 and add to 60. You see, because what does multiplication mean anyway? If you don't have a multiplication table, multiply to 899 means I will be finding two numbers to square and subtract their squares, and that's going to be my 899. And what's that big number that I square? The big number that I square is the average of the two numbers that I multiply together. Thank you for telling me what the average is. You told me the sum is 60, so the average is going to be 30. I already know that. I'm just actually showing you how if your brain becomes used to thinking of multiplication as find the average of the two numbers you want to multiply and subtract the square of the gap, square of half the gap, then if someone tells you the sum is 60, then you say, oh, yes, so the average is 30. Boop, done. And that's it. What about non-integer average? Thank you for asking. Since you asked that question, I'll tell you. I was trying to skip over it just because of both time and also we have younger people in this audience. But suppose I had 21 times 26. Uh-oh, can't do that anymore. Yes, I can. It is 23 and a half minus 2 and a half times 23 and a half plus 2 and a half. Now you might say, this looks horrible. Now I need to square the halves. Well, actually, look at what this is. Just a second. This is 23 and a half whole thing squared minus 2 and a half whole thing squared. Let's clear this off like this. And actually, it turns out they also had tables. Well, you see, yes, somebody had said you can also do 21 times 25 and then add a 21. That works. but they actually also had tables of the half-integer squares. The reason is because you can use some math to figure out all of these half-integer squares are nice. It turns out that if I wanted to know what is 1.5 squared, that's just equal to 2.25. And if I want to know what is 2.5 squared, that's equal to 6.25. If I want to know what is 3.5 squared, that's equal to 12.25. There's even like a rule to figure these out. But you see, if they all end with a quarter anyway, they do, by the way, they're all like whole numbers with a quarter, that's easy. Just like if you had a table that says, here are all the squares of the half integers, and they're all like whole numbers with a quarter, subtract the quarter away. Okay, so what this is trying to show is that, we had some fun talking about this math topic today. In some sense, this probably looks more like a math class than the kinds of things that you may have been used to at Museum of Math. In fact, usually when I'm at Museum of Math, I try to talk about something which might even be like relating math to real life. But at the same time, because of this rare opportunity where, it's not that often. It's not that often that there is an idea that could potentially go into every single Algebra 1 textbook in the entire world. And in the year 2020, you'd have thought that we should have everything already figured out. And this is not even a question about using technology. It's not like I invented the graphing calculator. Rather, I'm just suggesting that we insert in something that was part of the standard way that people did math 3,000 years ago. And with that 3,000 years ago technique, you're suddenly able to turn some questions which had guess and check in them into systematic ones. Let me make a very clear comment though. Quadratic formula is still faster. Completing the square is also correct. And in fact, completing the square is fundamentally important when you do later things in algebra. So you have to learn that anyway. What I just talked about is not a replacement for those. On the other hand, I came up with this presentation because I know from experience that if you take a first-time average learner of algebra and you try to move into completing the square, oftentimes it's a big hurdle to jump over. And what I found out in my experience is if you do this thing that I just did with some normal numbers, then people start to get it. And then you can just tell them, this completing the square thing, it's just what you've been doing. You've been doing completing the square with this entire hour without knowing it. And when it comes time to learn that, it just clicks easier. Okay, and so that finishes my part of the talk. I don't know what was the plan for the remaining session, the remaining part of this talk, in the sense that I don't know if there were Q&A that people were interested in. I happen to have this situation where we have this chat connection. I personally am happy to stay on and answer just maybe 5-10 minutes of chat that comes through this Q&A. And what will happen is that if you put a question into the Q&A, I'll just go and grab it and start giving some answer. And I can do this until maybe about 8:10 or 8:15, after which we have to get back to launching this coronavirus app because this is a serious epidemic that's hurting a lot of people. Okay. Well, I really enjoyed having all of you guys here too. If you have a particular question, I'm really happy to answer it. And I'm actually only looking at the Zoom chat right now. If I don't see something come in soon, what I will do is I will switch over to turn it back over to Cindy Lawrence, the executive director. So Cindy, it looks like actually we tied up everything pretty well with the Zoom chat. So if you would like to make some final comments, what I'm going to say right now to the rest of the YouTube audience is it was great talking to all of you guys. I hope you had some fun, and I'm going to switch off my broadcast on the YouTube. And for people who are on the Zoom, what you're about to see is I'm about to switch over to the Zoom. And when I switch over to the Zoom, what that means is that you'll have to turn you don't have to do anything with volume. I will simply unmute, and I will also open my camera onto the Zoom, and we'll switch over there to wrap up. So I'll see everyone. And yes, actually, if we had some YouTube audience here, we'll be back to normal programming tomorrow. As you know, I do the Ask Math Anything every day, and so there will be another live stream tomorrow at the usual time, 4 o'clock to 5 o'clock Eastern Time. And that one will be the usual format, where I will interact directly with the YouTube chat. See you all.